introduce Mike Luby. He is vice president in Qualcomm. Mike is a theoretician, but he makes his life actually his contribution to practice. And I remember his theoretical stuff on Arashia Code, and that's how, as I understand, he started his first company, Digital Fountain. Mike has a bunch of awards, from Hamming Award and so on and so on. He's also a member of National Academy of Engineering. Mike, please.
Thank you. So it's a great pleasure to be here. Thanks for having me on such short notice and everything. Today I'm going to talk about a mathematical theory of distributed storage. And this is based on some work that comes from practice. So it's kind of, in some sense, in the spirit of Shannon, in the sense that he went and looked at a lot of practical problems out there, and then he came up with this really beautiful information theory. I'm not saying this is as beautiful as that, but it still has the same sort of roots. So I think you guys are probably aware that there's all these companies out there that are having massive data storage deployments. For example, Facebook, Amazon, Microsoft Azure, Google. All these guys have hundreds of thousands to millions of computers. And they're using, and as you also probably understand, the requirement for data storage is going up over time. So in fact, today, a typical cluster can contain thousands of storage nodes. Each node, for example, has 500 terabytes of capacity. So these things are getting huge. And the clusters are built on commodity hardware. That's kind of a change from the past when everything used to be based on RAID kind of things. But now these are such at a massive scale that just doesn't scale. So they're actually building these clusters on essentially commodity hardware, where failures are actually quite frequent. So these nodes die all the time. Systems die. And so the idea is to put the reliability at a much higher layer across the whole system instead of on individual nodes. So the durability of data, one of the requirements of these systems is that durability. Durability just means the data is going to be around for a long time. You're not going to lose it. So a typical way that people do it is via replication. So they make 3 copies of the data and store it in 3 different places. And if one copy dies, they go and take one of the other 2 copies and make another replica. So that's kind of basically the old style of doing things. And obviously that has some costs associated with it. You need 3 times the infrastructure. And one of the more important components in the whole thing, everything scales. The costs scale according to how many nodes you have, how much capacity you have. So 3 times the copies, 3 times the storage is way too costly. By the way, this is a picture. This is probably even an old picture of a data center. I don't know if you've ever seen one of these. Actually, I want to go see one of these at some point. But they're pretty amazing from what I can understand. Just rows and rows, racks and racks of these storage servers. And then on the right, there's a graph that shows at each point in time over a month of how many nodes are down in the system at that point in time. And this is a 3,000 node Facebook cluster. And you can see that typically there's like 50, but it can spur up to 300 nodes down at a time, something like this. So obviously this can cause some issues. So here's kind of what people have been doing. As I mentioned, a lot of people are still doing triplication. Has a high storage overhead. 67% of your capacity is for overhead, and that's a cost. And in fact, it has some limited durability. If you get 2 failures, that's the most you could sustain. If you get 3 failures and you haven't copied in time, you lose the data, and that's it. And because of this, they have to do something that I'll refer to as reactive repair. When a data node goes down, they have to very quickly make a replica from one of the 2 remaining nodes. Otherwise, they're going to lose that data if any of the other ones fail in the meantime. More and more people are moving to using erasure codes. Reed-Solomon codes are probably the most popular choice. For example, there's some Microsoft deployments that use 963 codes. That notation means that there's 6 source pieces. They take an object, break it up into 6 pieces. They encode 3 redundant pieces, so there's 9 pieces total. So in this case, they can, as long as they have any 6 of the 9 pieces around, they can recover. If they lose more than 3, then they lose the data. Okay. And a similar configuration for Facebook. All these companies use all kinds of different parameters, but this is the one that's pretty popular. 1410.4 code where there's 10, take an object, break it into 10 source pieces, create 4 redundant pieces, and put those 14 total pieces spread over 14 different nodes. So in that case, you can withstand any 4 nodes failing and still be able to recover. 5 fail before you've repaired it, you lose it. Make sense?
Quick question, Mike.
Yes.
On the previous slide, that 50 number seems very high.
Yeah.
Are these failed stop? Are these transient?
So the question is, that number on the previous slide seems high, number of failures. And it is kind of high. And they don't give exactly why, but if you look in the literature, 90% of the failures are transient.
Yeah, that's right.
And so that means probably 90% of these are not permanent failures, which makes another interesting talk and another interesting thing I could talk about, but I'm not going to today. Actually, I think I'll mention it, but it's not a big part of this talk. It's really another talk. But that's a great question. Yeah, it is a lot. But they do software upgrades, rolling software upgrades. These things just crash. All kinds of things happen. Often they come back. The amount of times it takes for them to come back can be variable from 10 minutes to 6 days, something like that. And there's all kinds of issues associated with that. Okay, so going back to this slide. So here are some metrics by which you can measure a system. There's obviously storage cost is one metric. How much overhead do you have to sort of dedicate in your system to making sure you keep the data around. Repair cost, that's how much repair traffic you have to sustain to kind of repair things when things fail. Durability is an important one. You want to kind of make sure that you can keep this data around for a long time. That's the whole purpose, is storing it. And access speed, how fast can you actually access the data once it's stored. And sort of going toward, ideally, you'd like to have low storage costs, low repair costs, high access speed, and very high durability, right? Those are kind of the ideals. And there's different trade-offs between these triplication systems and small erasure code systems. Again, that's a whole nother talk. I'm not going to really emphasize that. We've introduced a new kind of system called the liquid cloud storage system, which is a combination of 3 main ingredients that kind of work together. One is using large erasure codes, such there's these Raptor Q codes out there that are part of an IETF standard at this point, IETF 6330. There's something which we call lazy distributed repair. Instead of this reactive repair where you immediately repair stuff, instead you do a background process and do the repair very slowly in the background. And then you use a different data organization for how you store it and access it to kind of make the access speeds much better. And in every one of these dimensions, we think we have an improved system. But that's really not the main focus of my talk today. Well, actually, there is one more slide. I forgot about this slide. So here's this is important because this is we've run a bunch of actually, we did a prototype of our system. We've written simulation software. Obviously, if you run a prototype in real time, you can't test the durability of system to 1 billion years. We just don't have that long to run the simulation. So we've built simulation software where you speed things up by factors of millions or more, so you can run things in a day that really span 1 billion years of real time. And run these simulations, and in this graph shows the different systems. There's triplication up in the upper right. There's the Reed-Solomon in the middle, and then there's a liquid system following that curve there. So the curve is a mathematical curve, which we could figure out, and then the points on the curve are simulation points. And you see that the simulations pretty exactly match what the mathematical theory predicts. And I should have said the x-axis is the storage overhead. That's how much of the capacity you've devoted to the overhead for storing your data in the system. So higher is worse towards the 0. X-axis is the 0 is better. And then the y-axis is the amount of repair bandwidth you need per node in megabits per second. And again, higher is worse, lower is better. And the y-axis is on a logarithmic scale, so each major tick there is a factor of 10 more. So this is pretty dramatic differences in terms of the amount of bandwidth you need for these systems. And then there's also the other aspect, which is the durability. So it's usually measured in something called mean time to data loss in the literature. This is how many years on average can you sort of keep all your data around without losing any of it. So higher is obviously better. So there's a lot of advantages for the system we had. This was really the inspiration for doing really what is the main part of the talk I want to give today, which is more of a theoretical talk than this more practical work that sort of started all this. And in fact, what we sort of introduced today is a mathematical model of distributed storage, which is based on this understanding that we've got over the last couple of years of how deployed systems work and how they really operate. And it models a distributed storage system where the recoverability of the message is maintained when nodes can fail, and it enables an exact analysis of storage overhead and repair bandwidth trade-offs. So there's two main parts to this theory. One is the lower bounds. These are information-theoretic lower bounds. It says that there's no system, no matter what you do, that can do better than this trade-off. So these are kind of fundamental bounds. And then there's the matching algorithmic upper bounds, which is an algorithm that implements something that has these trade-offs. And these actually use standard erasure codes. And as I'll explain later, these kind of lower and upper bounds are actually pretty close to each other. So how did I come up with this model? We've been working on all this practical stuff for a couple of years, and then I guess it was last November, I was invited to give a lecture at UCSD called the Shannon Lecture. Okay, UCSD, the Shannon Lecture. You better say something that's relevant to Shannon. So that's when I really started thinking, I wonder if there's an interesting theory that can be sort of introduced around distributed storage. And so here's the standard Shannon model that probably you all, at least most of you, have seen before, where you've got a source, it generates a message X that you want to get to a destination. You send it to a transmitter, it generates a signal, goes through a noisy channel, you get a perturbed signal Y at a receiver. The receiver tries to decode the original message, it produces a message Z, and provides that to the destination, and you're successful if Z is equal to X. Okay, so this is kind of just the Shannon model. So here's the sort of analogous distributed storage model, where you've got a source, it generates a message X, there's something called a store, which writes the data into these nodes. Some amount of time goes on where nodes fail, things happen, and at some later point in time, you have an accessor which reads some data from those nodes, tries to generate the original message X, produces a recovered message Z, and it's successful if Z is equal to X. Okay. So in this sense, it's very analogous. So what about those nodes? So this is kind of the distributed part. The number of nodes is, you don't just have one node, you have multiple nodes. Let's say n is the number of nodes. Okay. And they fail. So nodes can fail. So when they fail, you lose all the data on them. And you can replace it with an empty node that has all zeros on it. But you've lost all the data that was stored on that node, which is pretty much what happens in practice. So then you've got this idea of there's this repair that's running. And what the repair does is it can access data, read data from the nodes, do some computation on that using a small local memory, and write data back to the nodes. And its job is trying to protect the data so it's always recoverable, even though these nodes are failing in the meantime. Okay? So it's continually reading data from the nodes, doing some computation on it, generating some function of that read data, writing that back out to the nodes. And its job is to try to make sure that at any point in time that the original message can still be recovered with what's stored on the nodes. Any questions? Does it make sense? Okay. And so one of the metrics we're going to look at, okay, how much data it reads and how much data it writes. It turns out how much data it writes is pretty straightforward. The amount of data it writes is pretty much how much data is lost over time. But what's more interesting is how much data it needs to read, which is usually the dominating factor in terms of how much repair traffic there is. So that's the more interesting aspect to look at.
So can I ask a question? So you
Yeah.
read sequentially this node or in parallel all of them?
What's that?
Do you read them sequentially, so node number one?
So in this very, very simple model, so this is really an idealized abstract model. So there's many things that aren't quite real, right? One is that there's a centralized repair. In a real system, you'd have a distributed repair, where you have repairers all over the place, and they're all reading from nodes and writing and so on, right? Another aspect that's not really that realistic is when a node fails in this system, it's immediately replaced with a new node that's initialized to zeros. In practice, what happens is a node fails, you don't even know it's failed for a while, and then once it's failed, it might be a few weeks later when it's actually replaced, or you put in a bunch of replacement nodes at once. So this is kind of an idealized model, but it captures some of the essential features of the real system. And then in the end, you can sort of explore new dimensions, and I'll talk about that a little bit at the end. Did that answer your question? Sure. Yeah. OK. So when a node fails, all data stored at the node is immediately lost. In this model, the failed node is immediately replaced by a new node. The bits of the new node are initialized to 0, so you've lost all your data. But you can write new data to that node, of course. The failure process determines when nodes fail and determines what nodes fail. That's really the two most important aspects. When do they fail? What fails? And so here's a kind of a system overview. This kind of recapping where we are already. So the store writes data to the nodes generated from the message X received from the source. The repair is aware of when and what nodes fail. And it runs this repair process continually in a loop. It reads data from nodes, generates new data from the read data, and writes data back to the nodes. And then the accessor, at the point you want to access the data, which may be 2 million years later, it reads data from the nodes and tries from that read data to generate the original message Z. And you've succeeded if Z is equal to the original message X. OK, everybody on board? Happy? OK. Happy is the wrong word. Understand. OK, so the bounds. The lower bounds show that there is a failure process that for any repair, the average repair traffic is above a threshold function of the storage overhead. And this is an information-theoretic lower bound. And then the upper bound says there is a repair so that for any failure process, the peak repair traffic is below a threshold function of the storage overhead. And the upper bounds are based on this liquid cloud storage algorithms. It's algorithmic, which uses the combination of the large erasure codes, the lazy repair strategy, and flow data organization. So the failure process, let's get into just a touch more detail about that. Again, the failure process is the one that determines when nodes fail and which ones fail, or what fails. OK. So the timing, there's kind of two simple models that considered here. A fixed timing, which is very simple. At each delta units of time, a node fails. And then random. So with a Poisson distribution where the average duration between failures is delta, you just let that run. So those are kind of, T fixed is the fixed timing, T random is the kind of Poisson random timing. And then for the pattern determines what nodes fail, two are considered random pattern, which just randomly fails a node out of the n available at each point in time when a node fails, or an adversarial pattern, which means that you can pick a failed node chosen based on all available information and really does it in the worst possible way to make the repair work as hard as possible. And so if you look at all four combinations of these different failure process, by the way, there's more than this. I just simplified it down to these. These are kind of the ones that are interesting to talk about for today. The strongest one is the random timing and the adversarial failures. The most benign one is the fixed timing and the random pattern of failures. And then the other two are in between, where probably the one in the green there is the random. That's probably the one that people understand and analyze the most in practice, because that's kind of what a real system sort of behaves like. It's really random timing with random failures. There's a lot of caveats to that, but that's one that people kind of really try to understand and analyze a lot in practice. And then there's this other one, which is a fixed timing adversarial failures, which is actually interesting for other reasons. So these kind of form this partial order. The two in the middle are incomparable to each other. The one at the top is the strongest strongest failure process. It's the one that's hardest to work against. And the one on the bottom is the easiest failure process. Is the one easiest to work against.
So,
yeah.
That's a question. So
Yeah.
I think there can be some timing which is not random but rather adversarial.
Yeah, and that's another model which I didn't put up here.
Okay.
Yes.
Okay. And
Absolutely. And there's others as well. Yes.
And I assume you also don't assume that the bit flips can happen, so that the data is there, but it's just giving me wrong.
Yeah, so there's no errors in the data in this one. And I'll mention a little bit about that. Actually, in practice, that's a big deal. One of the big deals in practice is not just node failures and you know about it, but data is silently corrupted. And you don't know about it until you read it. Oh, sorry. The question was?
Oh, shall I? Yeah, so
Just remind me.
the first question was regarding the adversarial timing.
Okay, so first question was about adversarial timing. And that's another. So there's no, the timing here is fixed or random. And then there's also an adversarial timing model, which is mentioned in the paper that I'm writing, but is not mentioned in the talk. It's also interesting. And then the other question was?
Regarding the bit flips and the
oh, yeah. So
data corruption.
the other question was, well, could there also be bit flips and data corruption on the nodes that you don't even know about? And the truth is, yes. It can happen. It does happen. In fact, there was a talk recently by the lead engineer at Dropbox who just mentioned that in his talk that they actually scrub all their data every week and a half for exactly this reason, right? Every week and a half, they read all the data in their entire system and figure out if any of it's corrupted. And if it is, they fix it and write it back correctly. And it's exactly for this reason. And the reason is that this silent corruption is such a big deal is when a node fails, you know it, and then you know how much time you have to react, right? When something fails silently, it might have failed 2 months ago if you haven't read it in the meantime. And in the meantime, other pieces of data that are actually relevant to that one for all the data being lost could also occur, which is why they read it on such a regular schedule every week and a half going through everything, because otherwise they just might miss some corruption. And others do similar. They won't exactly tell me how long, but Microsoft guys, they all do scrubbing. Microsoft does it not quite as frequently, but not that infrequently. So they all do it.
Then there's one more question, right?
I'm sure there's more than one.
Correlated failures. So for example,
Yes.
if you have
Absolutely.
10 nodes sitting in the same rack, they're more likely to fail together.
Yeah. So again, this is a very simple model. Great question. So the question is correlated failures between timings of nodes. And absolutely, that's a big deal. In fact, one of the things that happens is that 10% of your infrastructure goes down at one time. And that's happened. Microsoft has mentioned to us that that's happened a few times. Also, what can happen is you get a new batch of equipment. And that new batch of equipment doesn't exactly have the same characteristics as your old batch. And suddenly, you have 10 times the error rate that you had before, right? So suddenly, your average rate even goes wildly up. And it can go wildly down as well. So all these things can definitely happen. I guess that really was the last question.
But then there's network partitions.
Yes. Network partitions, yes. Failure of the router infrastructure, yes. In fact, one thing that people are moving to now is geo-distribution, which is another aspect of this whole thing. So there's a lot of other interesting aspects to all this stuff. But let's go back to the very, very simple model here and go back to repair. So there's really two basic repairs that are talked about here. Actually, later I'll introduce another one, but right now there's just two, deterministic and randomized. Deterministic, the previous failure process actions determine the next repair action. Right? Everything's deterministic. Okay. Randomized repair can use the source of random bits to determine its action. Those random bits are private to the repair, not known to the failure process. Okay? Of course, the failure process can know some of the random bits by the behavior of the repair, but only once it acts, not beforehand. Right? Okay, so the first one I'm going to be talking about is this fixed timing. So the very simple failure model. So the timing of the nodes is on a fixed pattern every delta unit. Some node fails, but it's picked in an adversarial way. Which node fails is an adversarial way. And this is going to be working against a deterministic repair. And there's an upper bound and corresponding lower bound. And these are bounds on the storage overhead versus the repair traffic. That should have said what that trade-off is. So these are going to be bounds that show that if you decrease the storage overhead, you're going to have a consequent increase in the amount of repair traffic you're going to need to have, which sort of makes sense. And the bounds are equal asymptotically as the storage overhead goes to 0. So that's the interesting case, by the way. As the storage overhead starts going towards 0, that's when that's where people would rather operate rather than getting higher and higher. The whole point is to reduce the storage overhead because that's a major cost of the system. And let's see how much the repair bandwidth repair traffic has to go up as a consequence of that is really the question. And then the main bounds are going to be similar, but the main upper bound is going to be between a deterministic repair, which is the weakest repair, against the strongest adversary that I've talked about at least, which is this random timing adversarial with adversarial failures, right? So that's kind of the strongest bound you can have, the weakest repair against the strongest failure process. And then the lower bound is going to be against the weakest failure process, fixed timing random failures, working against a randomized repair, the strongest repair around. And so that's the strongest kind of lower bound you can have. And in fact, one thing I wanted to mention is that both of these bounds apply to the one that people consider in practice often, which is these random failures with random nodes failing. Random timing, random failures. And these bounds are equal asymptotically as the storage overhead goes to 0 as well. So that's kind of where all this is going.
How realistic it is that the overhead goes to 0?
What's that?
How realistic it is that overhead is going
I'll show you some
Okay.
bounds, don't worry. We're not done yet. You need to know what we're talking about before I can tell you how realistic they are. So here's really the slide that has the, if you want to pay attention to one slide that has definitions on it, this is the only one you really need to. And it looks kind of complicated, but it's not. So there's really, the storage overhead is which portion of your storage is really dedicated towards overhead. And how do you measure that? You don't assume coding or anything, but you do have a message size X, which is in this talk M. And you have a total capacity for storing things, which is C, which is just the number of nodes times the storage capacity per node S, right? So C is the total capacity you have in your system. M is the size of the data you want to store. So your storage overhead is just 1 minus M over C. And if you think about that, that's the percentage of your fraction of your system that's dedicated to storing stuff that's not your message. Okay. So that's one fundamental thing you need to understand. It's the storage overhead, and I'll always denote that as beta. And then the repair read rate, there's really 2 read rates I'm going to be talking about, and they're really essentially almost the same. One is going to, our averaging, we're always going to do lower bounds on the average repair read rate. And the upper bound is always going to be on the peak repair read rate. Okay. So peak means that you're going to put an upper bound on the bandwidth at any point in time and say you're never going to use more traffic than that. And average just says, well, over a certain duration of time, you're going to be using at least this average of read rate. Okay. And then durability is just the mean time to loss of at least some of the message until it's unrecoverable. So this is really, you want to sort of look at the trade-off between the storage overhead and these repair read rates, but keep the durability high. That's essentially the idea. Yes?
MTDL, is that the time until you expect that some message in the system is unrecoverable or any?
So in this talk, there's only one message. I'm just thinking it was a big blob.
Okay.
And it's to any portion of that message not being recoverable. So for example, the capacity of the entire system could be, 100 petabytes. And your storage, your message is 90 petabytes, right? In that case, your storage overhead is 0.10, 10%, right? And then your rates might be several gigabits to terabits per second. And your durability might be, 10 billion years until I lose any portion of this message, right? By the way, you might think that 10 billion years, why would we care about something like that? Well, people don't really want to keep the data around for 10 billion years. We're not going to be here in 10 billion years probably, right? But the point of that is that it's really a measure of how likely you're to lose it in the next year. And you want to keep that probability really, really tiny. So if it's 1 in 10 to the 9th, of losing any data over the next year, people are probably okay with that. But they're really not going to try to keep it around for 10 billion or a billion years or whatever.
So Mike, just
Yes.
to understand better, if you
Yes.
have 90 petabytes of data
Yeah.
and 100 petabytes of storage,
Yeah.
of course these 90 petabytes would be in a large number of blobs.
Yes.
And
In practice,
each-
yes.
In practice.
Absolutely.
And each blob will only be partitioned among a much smaller number of nodes than the number of nodes in your data center. So
Maybe.
For example, the blob might only be partitioned into 100 blocks, and the 100 blocks may be erasure coded.
Yes.
Is your assumption that each blob is striped across every one of the nodes in your data center?
So for the lower bounds, there's no assumption about coding at all. It's all information theoretic, right? There's no.
So this is not assuming any linear coding?
No.
Okay.
These are, so in fact, I should have said, I'm really not going to be even telling you what the question, yes. Okay, sorry. So, by the way, that was another question. Okay.
I do ask a lot of questions.
Yes, no, that's good. So the question was, if you have a large message in a real system, it's broken up into a bunch of smaller objects, and that's true. If you had 90 petabytes, you wouldn't just have one 90 petabyte object. You'd probably have, 90,000 1 gigabyte objects, or 90 million, whatever it is. And then when you encode those objects using some kind of system, you probably wouldn't spread it over, 10,000 nodes. You spread it over 100 nodes maybe, or 20 nodes, or whatever it is. All that's true. But what I'm talking about are information, at least what I'm talking about today, is information theoretic lower bound that says that independent of how you code the data, doesn't matter. Has nothing to do with coding, doesn't have anything to do with linear codes or anything like that. It's just really information theoretic lower bound that says that you have to use at least this much repair data. And the reason that's interesting is because then you can go back and look at some of those practical systems and see how they measure up compared to this, and see how close they're coming, right? And so one of the things that we used it for was to compare our liquid system against these lower bounds against existing systems. And the only previous technique we had to do that was to do these simulations and just say, look, here's how these guys work against our bounds. But we weren't really sure how close our guys, maybe someone else would come up tomorrow with something much better, right? And so what really one of the emphasis of this work is, no, there's this lower bound curve, trade-off curve that says no matter how you do it, you can invent, the newest coding system you could ever imagine. In fact, you can do something non-coding, something completely different. And you're still going to have this fundamental trade-off, because this is an information theoretic trade-off that has nothing to do with coding. Okay. Okay, so let me give you an idea how this is going towards your question, let's check. So here's an example of this fixed timing adversarial pattern of failures, of node failures bounds. So for example, when beta is 25%, which is pretty typical for a real system today, 25% overhead, then the lower bound says that the average read bandwidth has to be this fraction 0.815 times kind of this fundamental quantity S over 2 beta times delta. So again, S is the capacity of storage per node, is S. Beta is your storage overhead, and delta is the timing between nodes. So it says you absolutely need to have an average read bandwidth that is at least 8/10 of this S over 2 beta times delta in order to guarantee the message recovery. And if you don't, this adversarial repair failure process can fool you and make sure the message is unrecoverable. Okay, on the other hand, for the same storage overhead, there's an algorithm that has a peak bandwidth that's only 1.31 times this quantity, and it can guarantee the message recovery forever under this failure model. So those two are off by 50% from each other, something like that. So there's still a little bit of a gap there. Asymptotically, as beta goes to 0, they actually converge to the same fundamental bound. The 815 goes to 1, the 131 goes to 1 as the beta goes to 0. And then for the main results, so the lower bound is against this very benign failure process where the timing between failures is fixed, and just random nodes fail. And when it's interacting with a randomized repair, if the average bandwidth isn't lost, these are asymptotic bounds. I didn't put the constant in front of this. So that if it's got to be greater than this asymptotic quantity, that's necessary to achieve a large mean time to data loss. And then the upper bound is against this kind of malicious adversary where the timings are random and the failure pattern is adversarial. And it's interacting with just a deterministic repair, and the peak bandwidth is the same bound asymptotically to achieve a large mean time to data loss. So that maybe doesn't mean much, so I just tried to put some graphs together just to kind of visualize this. So the storage overhead here is on the x-axis going from 5% up to 49%, or 0.05 to 0.49. And the y-axis is, it's normalized, so I set s and delta to 1 just to take those out of the picture. So then the remaining formula is the access traffic bound. And so the upper bound is the sort of dotted one on the top. The 1/2 beta bound is kind of what it goes to asymptotically. That's the dark one in the middle. And then there's the 2 adversarial bounds. The kind of stronger adversary is the fixed adversarial. That's this long dotted one just below. And then the weakest adversary, which is the fixed timing and random failures, that's the one on the bottom there. And you can see even for larger overheads, they're not too far off from each other, but as they go to 0, they kind of start converging, and they follow this 1/2 beta curve. And then just to kind of visualize them here, what I did is took those same bounds, and for example, the upper bound I multiplied by 2 beta. So asymptotically, that should go to 1. And then look at the 2 lower bounds there, and they both should converge up to 1. And here the storage overhead is going from 25% down to 1%. You see as you get down there, they really start converging in a ratio. So this kind of answers the question you had, Watchdog. Okay. So now let's get on to what I think is the fun part, is to prove the lower bound for which turns out to be this game between the repair and the failure process. The repair is trying to ensure the message is recoverable. The failure process is trying to make the message unrecoverable. So there's this transcript, which is the record of all interactions between the repair and the failure process, which includes when nodes fail, what nodes fail, which bits are read by the repair, and so on. You can just think of this as a public record of whatever happened to the system as it evolves. So now this concept is kind of key for the lower bound. There's this concept of a snapshot. A snapshot is kind of what it sounds like. You take a picture of the system at a particular point in time. It's a kind of a snapshot of all the bits that are stored at the nodes at some time t. And then the question is, you want to look at what happens at some t prime greater than t based on that snapshot. And so these 3 things are defined. This is good to pay attention to these 3 ideas of this snapshot bits that are read between t and t prime. So that means that the repairer read them, and they had the same value when they were read as they did at t. And they were read at some time between t and t prime. Okay? And then the snapshot bits that are lost. So these are bits that were erased before being read at some point between t and t prime. These bits were just lost from the snapshot. You don't have them around anymore. And they weren't read by the repair, and that's key. The repair wasn't fast enough to read these bits. And then there's the bits that are unmodified. So nothing happened to these bits between t and t prime. They weren't read. The nodes didn't fail. Nothing happened. They're just sitting there. So you have these 3 things, they either read, lost, or unmodified between t and t prime. And these 3 quantities always add up to c, the total storage capacity of the system at any point in time, right? Because at any point in time, the snapshot bits have either been read, they've been lost, or you haven't touched them. Okay. Initially, everything is untouched at time t prime equals t, and you haven't read anything or lost anything. And then as time evolves, the red bits can go up when the repairer reads stuff. The lost bits can go up as the nodes fail, and the untouched bits obviously go down because now they've been touched, either been read or lost. But these three quantities always add up to C. And now the main claim to understand the lower bound is that if at any point t prime after a snapshot time t, the total amount of read bits plus unmodified bits is less than m, then the message is unrecoverable at that time, t prime. And there's another way of saying it is that if the lost bits is greater than your storage fraction times your total capacity, so this is the portion of your system that's been allocated for redundancy, if you've lost more bits than your redundancy, then the message is unrecoverable at some point in time, t prime. Okay. So let me give you kind of a quick picture of how that could just, if you didn't understand those definitions, here's a way of visualizing. Let's suppose you had a system where, a 9-node system where the message size happens to be the capacity of 6 nodes. Okay. And the storage overhead in this case is 3 nodes, right? 9 minus 6 is 3. Okay. And so beta is a third here. So let's suppose that this node fails. Red is failed. And then the repairer reads all the bits on this node 1 here for some reason. And then another node fails too. So when they're not overlapping like this, when the node fails, you lose all the bits on the node. They're all lost, right? And then the repairer maybe reads 2 nodes, and then another node fails. So you lose everything on that node. And then a repairer reads another node, and then let's suppose another node fails. Can you tell me anything about the recoverability of the message at this point in time? Is it possible that I could recover the message?
In an erasure code sense, you couldn't, but...
But even in an information theoretic sense, you can't, right? Because the number of bits that you've lost too many bits from the system. The total number of bits you could possibly know about are all the blue things plus the white thing. The red things you've lost before you even touched them since the time of the snapshot. So you've lost 4 nodes of data out of the system. But you only have 3 nodes of redundancy. So the point is that you can look at it 2 ways. I've lost more than my redundancy, or the amount of stuff I can possibly know about in terms of bits is at most 1, 2, 3, 4, 5 nodes of data, even if the repairer is lucky and reads that 7th node before the failure process comes and fails it.
Is the message assumed to be minimal in the first place? Because the message itself might have redundancy.
Yeah. No, let's assume it's...
Okay.
Yeah. So this is an example where the message is definitely not recoverable. Well, let's go back up a little bit. Let's suppose that the repairer happened to read these 2 nodes since the time of the, this is the pattern. So it's read these 6 nodes, and those 3 have been lost. Well, now we don't know. Message may be recoverable, but we certainly don't know it's lost. Right? Okay. So this gives a nice and simple analysis. So let's suppose for a moment that the erased bits and the bits read by the repairer are disjoint. Now, it doesn't really happen in practice, so we have to deal with that eventually. But just for now, just to get some intuition, let's suppose that whenever a node fails, it's erased, and none of the bits on that node have been read by the repairer at that point in time. And the repairer obviously just reads bits from nodes that have not failed. Okay, so they're completely disjoints. That means that all the erased bits are lost, right? Whenever you lose a node, all the bits you lost, all the bits that are erased are lost because the repairer hasn't read any of them. So a necessary condition for message recoverability is that the repairer needs to read m bits before the failure process erases c minus m bits. That's what we just said on the previous slide at the bottom, right? You have to read it. The repairer needs to at least read m before the failure process erases the redundancy c minus m bits. So the failure process erases bits at a rate in general, of S over delta, because every delta time units, a node fails. And when a node fails, you erase S bits. So the failure process is erasing bits at a rate of S over delta. Every delta units of time using S bits on a node when it fails. That's just straightforward. So if you put those two things together, then the repair needs to read bits at a rate of at least m over c minus m. That because the repair needs to read m bits before the failure process erases c minus m. So it's m over c minus n times the rate of failure, s over delta. And you simplify that, you get 1 to the minus beta times s over beta times delta. So that's almost our lower bound, except for it's missing this factor of 2 in the denominator, essentially. And it has this extra factor of 1 minus beta in the numerator, which I don't really care about that much. So this is only a lower bound in the special case when the erased and read bits are disjoint. But in general, they're not disjoint. The repairer can read bits from those before they fail. The bits that have been read are not lost if that node fails. You've already read them before. So the number of bits lost when a node fails can be less than S. So let me just show you an example of that. Here's sort of, so in this case, the repair reads a little bit from each of these 3 nodes, right? And then some node fails. Now, when this node 1 fails, before we lost all the bits on the node. Now we don't lose them all. We just lose the red portion. The blue portion we've already read, so we don't lose those, right? We just lose the red portion. And then read some more by the repair. The failure process fails another node. Again, when that node fails, you don't lose all the bits. You only lose the red ones, not the blue ones. And then so on. Yes?
So when you read, then you are making sure that you're writing it to some new 10th node?
So the question is, when you read, you're making sure you write it into a temp node. This is the information-theoretic lower bound. So I don't care what you do with it. I just want to, so what I'm assuming is that there's no real assumption about what you did. It's just saying if you didn't, it's sort of the opposite. It's that if you didn't read them, you absolutely can't know about them. If you did read about them, probably be smart to do something with them and write them somewhere, right? But this lower bound doesn't argue about that. It doesn't really, implicitly, yes, probably you do write them somewhere, and you probably write them to that, or encode them in some way, and you write them to that red portion there where it's been replaced by a new node, right? And so on. But this lower bound doesn't even really care about what you do. It just cares about what you didn't do. If you didn't read them fast enough, you obviously don't know about them. But you're right that in practice, in an algorithm, if you're worried about the upper bound, if I explain how the upper bound worked, then obviously when you read them, you do something with them. You encode them in some way, and you write them somewhere else in encoded form, right? Make sure you preserve it, right? And make sure you keep as much information about it as possible. But for the lower bound, I don't have to worry about that. I'm just showing that, look, if you didn't do this, you obviously can't know the message. Okay. Yes, okay. Well, we're almost going to be done about 3 o'clock, don't worry. Yeah. Okay, so snapshot intervals is kind of important concept. So what I already defined the concept of the snapshot interval. You take a snapshot at some time t, and then time goes forward to some t prime, and between t and t prime is your snapshot interval. So what is shown here is we're going to devise some bound b on the average read traffic per node. So I'm going through the real lower bound now. When you can read from nodes, so when nodes fail, there might have been some data that is already read from them, right? That's kind of a key issue here. So the way this lower bound is going to work is we're actually going to look at failures of 2 beta n failures in a row. And we're going to look at how much repair traffic the repair reads between each node failure. And so we're going to have some bound b, which is what we're going to want to be the lower bound on its read rate. So b is the amount of traffic that we wanted to read between each node failure on average, right? And it's defined this way. fancy formulas. Don't worry about what they are. Essentially, the way to think about it, if you look at the first one there, this LBD of 2 beta is essentially, think of it as being equal to 1. So B is essentially S over 2 beta. Okay, so I get rid of that. So what happens, so now what we do, we took a snapshot, and then we see how much the repair read between the beginning and the first node failure. And say it read that much. It's below the average. And then it read a little more than average between the first and the second, but overall the average of those 2 reads is still not above the average, right? So we're going to keep going until the repair read traffic over the entire from the beginning of the snapshot until now is above this average, right? So in this case it is, right? If you took the integral of those blue rectangles there, the total area under them is going to be at least the area bounded by this red line, right? And so at this point we're going to say, okay, good. Bang, we're going to start a new snapshot at this point because the repair is read enough on average over this interval to be above my bound, right? So, and I'm going to define this interval to be high. Okay, so another thing the repairer can do is say, you know what? I'm not going to respect your lower bound. I'm going to just read below it all the time, and I go all the way out to 2 beta n failures. And the average read traffic per node failure since the snapshot is averaging less than B over all these 2 beta n failures. So I'm going to classify this interval as being low, right? So they have these 2 kind of intervals. High intervals are ones where the repairer read a lot of traffic on average, at least my bound that I want. And low intervals, it didn't read enough, below my bound. So here's how this adversary is going to work. It starts an interval and looks at all the possible node failures it could do. I could fail node 1 to start with, or node 2, or node 3, or node 4. And what if they all turned out to define, then it interacts with the repairer reads some data, and it didn't read enough in each of these cases. So they're all low intervals. Okay, do it again. I'm not going to expand them all out. Let's suppose it continued with node failure 2, and it failed next 1, or 3, or 4, and looked at all different possibilities, and they all turned out to be low again. Then done it one more, and then on the next round, from node 3, it fails node 4, and it turned out to be high. So now the adversary knows if it failed node 2, followed by node 3, followed by node 4, that leads to a high interval in this case. So this says that there is a path that leads to a high interval. So what the adversary does, the failure process does, is it chooses this path to define the interval. And by doing this, it says, okay, I'm going to fail node 2, node 3, and node 4, and end the interval there. And I've just forced the repairer to read at least the average over the interval because it's a high interval, right? Good. I'm going to end that interval. Over that interval, the repairer read enough. I'm going to start a new interval and start this whole game over again, right? Okay, there's one other thing that can happen. First node failure, it starts an interval, looks at all the possible first node failures, node 1, node 2, 3, all low. Looks at all the second ones, all low. Looks at all the third one, all low. Looks at all the fourth one, all low. And at the end, all paths over these 2 beta n failures lead to low intervals. Well, in this case, we're going to show that this implies the message is unrecoverable for at least one of these paths. And that's the path that this failure process is going to choose. It's going to choose a path that leads to the message being unrecoverable. Okay. So in the worst case, when all the paths define low intervals, which is the one of interest now, again, this B is the bound on average read traffic per node failure. The best way to organize it for all of them is to put an equal amount of read traffic per interval and make it always B. And I'm hiding a lot under the rug here, but that turns out to be the best strategy for the repair, is to always read right at this bound B at every read, no matter which failure happens. And then it also turns out that you can show that in the expected behavior, this is what's going to happen. The first node failure is going to happen, and then on average, when it reads, it's going to be spread equally over all the nodes because the repair is going to be, the failure process is going to be failing nodes randomly. By the way, it also turns out for the algorithm, this is the right read pattern. You do want to read equally from all the nodes, but that's sort of a side note. For the lower bound, this is kind of the expected value of the amount read from each node when every node reads B. So what this means is that you're reading B over n from each of the n nodes on average. And then the repair fails another node. And then the failure process, then the repair on average reads this much from all the nodes, and so on. This continues. It sort of continues until it stops. There we go. So what's the point of this? What's the lost data? The lost data is everything in the red. If you look at this picture, it's about half the area, right? That's kind of the key insight. Out of this 2 beta n total capacity, about half of it's lost, right? And that kind of explains where, half of 2 beta n is beta n, which is your overhead, right? And that says you've lost essentially your overhead. So here you compress this picture up. So this is sort of the same picture, but simplified slightly. So the total number of node failures is 2 to beta n. The total capacity erased is 2 beta n times s. The expected number of bits lost is at least half the capacity, so that is at least this c minus n is the overhead, right? And that's kind of the proof, the sketch of the proof of the lower bound. So this implies that there is a path where the number of bits lost is at least c over m, implies that the message is unrecoverable for the interval defined by this path. And the failure process chooses this path to define the interval, right? At the end of this interval, some part of the message is no longer recoverable. Okay, so kind of moving a little fast, well, not any faster, but not as much detail at this point. So this was a fixed timing adversarial pattern adversary. But the one we really kind of care about is not that. It's more, for example, fixed timing with random failures. And there's a few technical issues to overcome with that. So not all node failures are snap failures. So before, whenever a node fails, I assume it's one that was a new failure since the time of the snapshot. But generally, nodes, the same sort of node can fail again. And the second failure doesn't really do anything with respect to the snapshot. So that's what the first one is about. It's not really a very hard or deep issue to overcome. It turns out that most failures are snap failures when the storage overhead is small anyway, so it doesn't really matter much. Another one is that node failure timing variance. So the requirer may decide a strategy based on the timing between node failures. And so it turns out there is an argument you can make that show that on average, even short intervals have average failure timing. You can sort of remap the short intervals to a longer interval and so on. And then there's another, the main issue, and the really key issue here is that you're really, with this adversary, you have to worry about random failures instead of adversarial pattern. On the previous one, I could pick that pattern exactly to make sure that the message is unrecoverable. I don't have that power anymore. The failure process cannot choose which transcripts to continue and discard. It just goes forward with a random failure. So the previous argument shows that the message is unrecoverable in expectation. And that was kind of key to getting to this result because it was better than just saying there exists a path. It actually said on average there exists a path. And now you can strengthen that by using a submartingale argument to say transforms the expectation to a high probability result and say it's not just there exists a path, but almost every path you'll lose some portion of the message. Okay, and then this functional model is also interesting. This one has been, in some sense, studied in the literature, so I wanted to just quickly touch on that. So here's the nodes that we had before, and now we're going to give them additional capacity to compute a function of the nodes before the data is accessed by the repair. Now, probably most people in this room are not that familiar with sort of research in storage. But there's been a lot of research in using network coding in storage. And part of that research shows, for example, that there are storage systems that work really nicely if when you access data from a node, instead of accessing it directly and just reading the bits, you perform some function on that bit. So you take random linear combinations of the data on that bit and sort of compress it in some sense before sending it on to the repairer. And in those models, they only measure the amount of data read by the repair after those functions are applied, even though those functions typically operate on a much larger volume of data than they actually send to the repair. So in some sense, they're kind of cheating because they don't really read the data, count the data that's read from the node. But nevertheless, it's an interesting model to consider. So in this model, again, you only count the data that's read by the repair. You don't count the data that goes from the node to its function. That volume of data could be much higher. So the functional model is it's a generalization of the previous case. So the previous model is a special case. It allows much more powerful repairs. They can perform arbitrary local node computation on the data before provided to the repair. So the local network traffic between the node storage and the CPU at node doesn't count in the read traffic. It allows the repair to do things like network coding. There's this famous paper on regenerating codes by Demakis et al. That looked at doing things like this. It allows arbitrary techniques at the node beyond using standard erasure codes or even network coding. So one of the interesting things about this is that even with this extra power of these functional nodes, the lower bounds are the same. There's no difference in the lower bounds from what I said before. The lower bounds that I stated before also apply to this functional model in terms of the read rate, in only measuring reads from the repair. So the upper bounds use standard erasure codes and read directly from the nodes, and the upper bounds match the lower bounds. So in some sense, this implies that network coding is unnecessary to achieve the optimality. You really don't need to do this functional model to achieve these trade-offs between the repair traffic and the storage overhead. And then this is some of the questions that kind of came up in the beginning. This is a very basic model that I talked about today. It's as simple as you can imagine. So there's all kinds of other interesting things to look at. For example, transient failures, as I mentioned in the beginning, 90% of the failures in a real system are transient. Node goes down for a while, comes back at some point. And there's often a delay between the node failure and when that node is scheduled for repair, because you don't want to repair transient failures. If a node goes down and you start repairing it and then it comes back up, all that repair traffic you used is useless. And if you did that all the time, 90% of your repair traffic would be useless because 90% of your failures are transient, right? So they really have to be very careful about setting these timers, typically set to 15 minutes to 30 minutes kind of timing before, from when a node fails to when it's scheduled for repair. And this can be a real issue. So that's something interesting to look at in terms of augmenting the models to take that into account. The silent data loss, someone asked a question about this earlier, I think it was you, where you don't even know the data's lost until it's lost. So you need to read the data to know whether or not you lost it. And that's a big problem because if you're not reading the data often, you can sit there and silently corrupt, and then some other portions of it can corrupt, and you don't even know about it, right? So this is something also interesting to add to the model and look at it. There's another issue that I was talking to somebody who's working with these real systems, and he mentioned that a real problem that people don't really talk about enough is this rebuild problem, which is you're always constantly upgrading your infrastructure with new stuff, right? You're kind of bringing down your old nodes and throwing them away because they're out of date, and you're adding in these new nodes into the system. So how fast can you do that? And in general, there's this sort of issue of nodes are often introduced in batches by a robotic or a manual process. So all these things are kind of interesting to kind of augment the model with. Another one that's key is in this model that I introduced is this global repair where all the repair traffic for the entire system goes to this repair. Well, these lower bounds also apply if it's a distributed repair. They just say how much repair traffic there is in the entire system. But it is very nice and a good question to look at that model more explicitly, where the repair is distributed through the entire system. In fact, these liquid systems that I talk about do have that property that you can do that, as well as all these more practical systems have some notion of distributed repair. So it'd be interesting to augment the model and look at that. And obviously, the idea is to avoid network hotspots and so on. Different failure models, I think you brought this up. Varying failure rate, correlated failures, all kinds of other things that can happen. All these things are interesting. Another thing that didn't happen is geo-distribution. That's another interesting aspect to add to the model. And there, the issue is often you don't want repair traffic going from one geolocation to another. So you have to take that into account when you design your model. Okay. And I think that's it. So thank you very much for your time.
We have time for some questions, but you have to use this one.
I was curious, in an actual application, I suppose that the choice of the model would depend on the hardware that's used, right?
So the choice of abstract model?
Yeah, how would you choose the model in an actual application?
Oh, so that's another interesting question. So one thing that comes up is that, so that probably affects, for example, this. So right here, that's very simple. This delta is the time between node failures, right? Where you model this by a Poisson. Practice, you don't know what this Poisson is, right? So you kind of have to learn about it as it goes on. It may vary, as I mentioned, over time, right? Some hardware has one rate, another hardware has a different rate. So that's another interesting aspect where internally we've done work on that, where we have algorithms which, for our stuff, automatically adjust the repair rate, not knowing anything about the system a priori. You just kind of understand what's going on as it happens, and it automatically adjusts and makes sure it remains durable, but uses as little repair bandwidth as possible given the current conditions. So that's something also that's important and crucial.
I'm sure you have a question.
So in these real systems, do you actually, when you reconstitute an erasure code, do you maintain the inverse explicitly, or do you actually on the fly compute the inverse? So for example, so you have the coding matrix, and at some point you lose a block, and so you have to effectively multiply by the inverse of the row of that particular coding matrix.
Right.
So do you always keep that inverse separately, and you know what the coefficients are, and you just sort of apply the coefficients to the blocks that you're getting, or do you actually do it on the fly?
So I'm not exactly sure, because I think you're getting down into a deeper level than the way I'm talking about it. But generally what happens is that each of these fragments that they store for, so you have an object, you break it into fragments, you store these fragments on different nodes. They keep track of the pattern of fragments and so on. And so when you lose certain ones, you know which coefficients are associated with those. And so when you read the other ones in, you know which ones you need to reconstruct, you know which ones you've got, and so you just do it. Yeah.
Any other question?
So at the beginning of the talk, you talked about this randomized repair, where the repairer uses some random bits, I guess, that to decide which nodes it will access to obtain the information needed for repair, or what are those random bits used for?
So so for the lower bound, you just want to make the repair as so. There's two questions. One is for the upper bound, one is for the lower bound. For the lower bound, you want to give the repair as much power as possible, right? And make the failure process as weak as possible and prove the strongest possible lower bound. So the reason for giving the randomized repair there is because obviously a randomized repair has more power, at least on the surface, than a deterministic repair, right? So you want to kind of say, I don't even know what that repair is, but I'm going to give him as much power as I can, and I'm even going to give him access to random bits that the failure process doesn't know about in case it helps him. I don't know if it can or not, but I'm still going to prove my lower bound even when he has access to these random bits. Now, for the upper bound, a randomized algorithm may be useful. It turns out for the algorithms that I didn't describe today, they're all deterministic. And in some sense, that's a stronger bound. So it's a stronger bound if you provide an algorithm that's deterministic going against an adversary that's as strong as possible, an adversary with randomized timing and so on, right? And so that's what the upper bound is that I stated but didn't prove in today's presentation. That's a whole nother presentation. I don't know if that helped, but
Yeah.
okay.
Any other question? Okay, let's thank the speaker again. Great, thank you.